Noise is the most fundamental limiting factor in a communication system. As we talked in the last module, a weak signal is not a limitation because we can amplify it. What we can't do is remove noise from a signal. So amplification isn't a way for us to improve the signal-to-noise ratio. So taking care of noise is probably one of the most fundamental jobs of the receiver. So let's talk a little bit about types of noises. Noise can come from a lot of different physical origins, and we're not going to talk too much about that. But there are a few noises that we've talked about so far in the class. One is thermal noise. It's also known as Johnson noise, and that comes from one of the earlier researchers that was able to quantify and do some calculations with this noise. And we call it thermal noise because it's the same as white noise, and it basically comes from the fact that objects that have any temperature above absolute zero have random motion, and that random motion causes noise. And we'll talk a little bit about that concept in just a minute. Flicker noise, this is something that we deal a lot with in electronics. It's called 1 over F noise, and it's a noise that shows up at low frequency, and it's typically caused by traps in transistors is one area where charge will get trapped and then randomly will get released, and that causes some low frequency noise. We don't deal too much in system level with flicker noise. Phase noise, we've talked about this before. This is the phase and frequency of an oscillator shifting very faintly as time goes on. It's easier to think about as jitter. I have a clock, and that clock edge jitters back and forth. Shot noise, this is something that happens in devices. Rain is an example of shot noise. And if you're wondering where does it get its name, it's literally from if you take a bunch of shot, which is small metal beads, and you were to drop them, the noise that comes out from hitting the floor, same thing as you'd hear for rain is where the shot comes from. So now we know a few types of noise, and I'll just mention that we're mainly going to deal with thermal noise, which is white. Shot noise is also white, and so we just talk mainly though about thermal noise because it's a dominant one for our systems. Put another way, you're always going to have thermal noise. You may have another type of noise, but you'll at a minimum have some type of thermal noise if you're above absolute zero. All right, so we're going to go into a little bit of math, and in the end, we're going to give you a simple equation to use. So if you can just bear with me as we go through. So noise, NT, is a random process. And when we have a random process, it's sort of like if you're at the roulette table. I can't tell you what the next spin is going to be. However, by using percentages, I can tell you that on average, the house is going to win 3% of the time. And that's just 1 over 36 or 35, depending upon where you are with the roulette table. So for random processes, we can't say much about its exact instantaneous value, but we can talk about average quantities. And for noise, average power is what we talk about. And it can be calculated by measuring the area underneath the n square of t over a long time. So the way to think about it is I have a random signal here, and I can never tell you if this is where we are in time right now. I can't tell you what that peak will be, what that peak will be, what that peak will be, because that's all in the future. So I have no idea what that is. However, if I were to take the power of this, and so if this was a voltage, I could take the voltage squared, and so the area underneath would be proportional to power. It turns out for a certain type of noise, this average power is actually constant. Okay, so this is the important thing. I can't tell you what the signal will be in the future, so I can't tell you what n of t plus 10 seconds will be, but I can tell you what the average of n squared of t plus 10 will be, and the reason is because it's equal to the average of n squared at t, because this doesn't change. And that's because the source of the noise generates a constant power of the noise. And we'll talk about that in a second. So the question comes, if I have to average this, so here I'm taking my average from 0 to t, in theory I'd have to average over an infinite time. And it turns out taking the average power over time is a very inconvenient way to measure noise. And so we don't do it in the time domain, we do it in the frequency domain. And this is with the noise power spectral density. We've talked a little bit about this before in some previous lectures. Since it's impractical to analyze noise in the time domain, we turn to the frequency domain. And so in this plot down here, we have what we've called before as white noise. And I've just drawn in here what 1 over f would look like. But we're mainly going to concern ourselves with this noise that's here. And so this random signal gives us this power spectral density. And if you remember, we talked about the Wiener-Khinchin theorem, and we could say that the variance, sigma squared, of this signal could be related to the power spectral density. Do you remember how we did that? We said that if we had a bandpass filter that filtered out a certain amount, the area underneath that curve would be equal to sigma squared. And that's how those two are related. And that's how we go between the idea of noise in the time domain to noise in the frequency domain. And if you're trying to figure out how do we do that, just go back to that idea that the average power for noise is constant. So whether I measure it in the time domain or measure it in the frequency domain, the average power is going to be the same. So really all I have to do is calculate, well, what's the average power? And that is the power spectral density integrated over a frequency. That's going to be equal to the total power of the signal. And n squared over here, which is related to sigma squared, is going to also be the total power. And I can equate those two through the Wiener-Khinchin theorem.